Okay,
Ready then?
we're ready.
Let us begin. So, well, we're here with Dr. Kayser right after he finished his lecture on neutrinos. And Dr. Kayser, that was quite a wonderful lecture.
My pleasure.
We'd like to ask you a few questions for those who could not assist to this conference, to learn a bit about your work and, well, particle physics in general. The first and, well, the question I believe you get the most is, could you please explain to us what a neutrino is?
Gee, I wish I could, but I'm going to try my best. A neutrino is one of the submicroscopic constituents of matter. There are very large numbers of them everywhere. We and all the things that we encounter in our everyday lives are made of other particles than neutrinos. They're made of electrons and particles called quarks. But for those particles that make everyday matter, neutrinos are very much more abundant. They are about 1 billion times more abundant than these other particles. The reason that we don't become aware of them is that they're very penetrating. They can travel through us as if we were not there. They don't notice us, and we don't notice them. But they exist, and without them, the sun wouldn't shine, and we wouldn't be here. There's also a possibility that without them, the universe would not consist of matter alone without any antimatter. And since matter and antimatter annihilate each other when they meet, it's a good thing that the universe consists of matter without any antimatter, or again, we wouldn't be here.
That's quite a complete answer, thank you. Now, again, on your favorite topic of neutrinos, last year's Nobel Prize, as you surely know, was awarded for the discovery of neutrino oscillations, which proved that neutrinos have mass. What are the implications of this discovery? Could you please let us know?
The discovery that neutrinos have non-zero masses opens some possibilities that would not have existed without those masses. One of those possibilities is that neutrinos, as I mentioned before, might be responsible for the fact that the universe contains matter without containing any antimatter. That grows out of the fact that neutrinos have non-zero masses. That could be a very important implication. Another possible implication has to do with the dark matter in the universe. That's something I didn't discuss in the lecture at all. But we know that there is dark matter, which we don't see directly, but we know it's there because of its effects on things we do see in the universe. And one of the hypotheses is that the dark matter consists of something called sterile neutrinos. And these sterile neutrinos have to have masses in a certain range. Again, the discovery of neutrino masses opens the door to that possibility. Those are two examples. There are others.
But I wasn't aware of that. Well, now that you talked a bit about dark matter, there was a recent announcement that, well, everyone is aware of, as far as I'm concerned, about the discovery of gravitational waves.
Yes.
Yes. So, in your expertise, could you enlighten us a bit about how does this discovery bring us closer to a more complete model of reality? Do you think there's any chance that we might encounter the graviton, say?
First of all, I think just about everybody in physics found the detection in the laboratory of gravitational waves to be an incredibly exciting event. We pretty well knew before this event that gravitational waves exist. We knew that indirectly from observing the energy loss of a binary pulsar system, which was visibly losing energy in a way that was attributable to gravitational waves. And the observation of that binary pulsar resulted in an earlier Nobel Prize. But there's no substitute for having a direct observation of what you think is going on to make absolutely sure that you're not somehow being fooled. And that was the direct detection in the laboratory, or more precisely, in 2 laboratories, 1,900 miles apart, of gravitational waves. So it was very exciting for that reason. It was also exciting for another reason. The detailed observation of these particular gravitational waves told us that the source of these gravitational waves was the collision of 2 black holes. Now we know that we have known for a while that black holes exist. There is a black hole at the center of many galaxies, and perhaps at the center of essentially every galaxy. We know there is a black hole at the center of our galaxy, and there are also smaller sized black holes outside of the centers of galaxies. But this is talking about 2 black holes that are revolving around each other, losing energy by gravitational radiation, and coming closer and closer and closer until they overlap, and then bam! And there's this emission of a lot of gravitational radiation, and that's what was observed. I must say, on a personal note, that the observation of these gravitational waves was exciting for me for another reason. I happen to have worked at an agency in the US government which is called the National Science Foundation for many years. The National Science Foundation funds science, obviously, and that is the agency that paid for the detectors that made this detection of the gravitational radiation. Now, I had nothing to do personally with the National Science Foundation undertaking the support of this program, but I watched my colleagues who did have plenty to do with it, and I saw what a challenge it was for them to get the National Science Foundation to spend what for that agency was more money than it had ever spent on any single program. In particular, one of them, Richard Isaacson, went to a lot of effort with his own knowledge of gravitational waves, which he had worked on in his own research, and with his savvy understanding of how you make things happen. And frankly, I don't think it ever would have happened without his efforts. So, although I had nothing personally to do with it, I watched what he did, and I watched what some of his colleagues did. And so it was exciting for me that now, after so many years, this investment that they made possible paid off in a very big way, scientifically. What the discovery will help us to understand about reality, I don't know that we're measurably closer to detecting a graviton. That's, of course, a very interesting goal. But now it is absolutely clear that gravitational waves, which may be carried by gravitons, exist. There can be no reasonable question about it anymore.
All right. Well, there's another huge project, CERN, of course, you know it.
Yes.
And it was only last year that they announced the discovery of the pentaquark.
Yes.
Now, would you be so kind as to explain to us what's the significance of this discovery?
We have a pretty successful theory which is called quantum chromodynamics of QCD of the strong nuclear force. which binds quarks together to make, among other things, the nuclei of atoms. Now, what we had seen in the past is that QCD binds a quark with an antiquark to make what is called a meson, or it binds three quarks together to make protons and neutrons and other similar particles. But we had not seen examples of where it binds 5 quarks or 4 quarks and an antiquark. In other words, 3 quarks and a quark-antiquark pair. A pentaquark is a thing like that. It has 5 quark-like things in it. And so to see this tells you about the possible things that quantum chromodynamics can do, other than the things that we have known for a long time that it does. So the pentaquark is a very interesting discovery.
All right. Now, going to a more personal set of questions. Say, could you help us answer, what exactly is it that the work of a theoretical particle physicist consists of? What is it that you do?
Yes, this is a familiar question.
It concerns a lot of people.
There are 2 kinds of physicists, basically, experimentalists and theorists. The experimentalists actually do the experiments. They carry out observations with dedicated equipment in laboratories. The theorists do calculations on pencil and paper, or sometimes using laptops or even supercomputers. They're not doing the actual measurements in the laboratory, but they are trying to invent theories of the reality as it is known. These theories have to predict new phenomena that have not been seen so far, and then you do experiments in the laboratory to see whether the predictions of the theory are correct. If they are wrong, the theory is wrong and it goes in the garbage can, or it has to be modified. If the predictions are correct, that is evidence in favor of the theory, and that's how physics works. It's a back and forth between theoretical physics and experimental physics. And theoretical physicists do many other things. When unexpected experimental results are discovered, which, by the way, happens all the time, and that's great.
That's fantastic.
Theorists then try to interpret what is it that has been discovered, and how does it fit together with what we already know. And given what has been discovered and how it fits, what new phenomena do we expect to see? And what sort of experiments could see them? Well, theorists are involved in all of those kinds of thoughts. And then I'd like to add to my answer to your question a little personal thing that happened to me at a party involving musicians. There were a variety of musicians at this party. There were some who actually played musical instruments, and there was one composer who was married to one of the instrumentalists, a violinist. And at one point in this party, the violinist came up to me and she said, "You know, there are 2 kinds of people in music. There are the composers, who write things on a piece of paper. But then there are the actual musicians who play instruments and actually make the music. Are there 2 kinds of physicists like this too?" And I said, well, in a way, yes. There are the experimentalists and the theorists. There are the experimentalists who actually make the experiments. And there are the theorists who, like the composers in music, think about the experiments, but they don't actually carry out the experiments.
was a beautiful answer. Now, lastly, are there any words that you would like to say to any aspiring particle physicists out there?
I think we live in a time that is very exciting for particle physics, and also very exciting for the astrophysics, which is related to particle physics in many ways. We've discovered in the last few decades amazing things that have radically changed our picture of the world. And so for people who aspire to enter a field like this, I would be very encouraging. I think there are wonderful opportunities. Who can tell where the field is going to go? It's been so amazing in recent years. I can only look forward to what's going to happen in the future. I'm no longer 25 years old, and I talk to my cardiologist regularly about, getting to the point where I see yet a few more things, but young people who are 25 years old, by all means, go for it.
All right. Then, on behalf of the Research and Innovation Students Association, we would like to thank you for your time.
My pleasure.
That would be all.